This is the fifth video in a series to support a course in complex analysis. We just got finished looking at the square function, the square root function, the exponential function, as well as the logarithm with the discussion of branches and branch cuts. And now we want to look at a power function in general. So let's recall that the principal branch of the logarithm, capital LOGZ, which is defined as long as the complex number z is not equal to 0, is given by the natural log of the modulus of z plus I times the argument of z, where here we're taking the principal value of the argument. Now, if we extend this to a multi-valued function denoted by lowercase log of z, we can say that log of z, lowercase log z, is equal to uppercase log z plus 2 pi I n. And these n run over all integers. And so that's because the exponential function has a period of 2 pi I and the logarithm is inverting the exponential function. Okay, so armed with that recollection, for alpha, which is a complex number, we want to define z to the power of alpha. And we'll define that as e to the alpha times log z, where this is not the principal branch, it is the multi-valued function. And so using exponent rules, as well as this definition up here, we can split that into e to the alpha times the principal branch of the log function times e to the 2 pi I alpha n, as n runs over all integers. And this guy right here means we possibly have infinitely many values for this power z to the alpha. Okay, so let's look at a couple of basic examples that have like some nice results, and then we'll look at some more exotic things. We'll start by proving that if alpha is an integer, that is equivalent to z to the alpha being single valued. So instead of having potentially infinitely many values, we really only have one value. Okay, so let's get to it. So we'll do this forward direction first. So we want to suppose alpha is in z. But now let's look at this z to the alpha via what we saw over here. And notice that's e to the alpha capital log z, in other words, the principal branch of the logarithm, and then e to the 2 pi I alpha n. But let's notice that if alpha is an integer and n is an integer, then alpha times n is an integer. But since this exponential function is 2 pi I periodic, that means this whole thing right here is just equal to the number 1. So we get that this guy is really just equal to e to the alpha and then the principal branch of the log. And then I'll verbally sketch out the reverse direction. So if z to the alpha is single valued, then everything of this form is equal regardless of the value of n. So that means it's equal to the case when n is equal to 0, which is the same thing as this down here. But now if this guy right here is equal to this for all n, then that means that this thing which I've boxed in blue is equal to 1 for all n. But that means that alpha times n must be an integer. Since n is an integer, that means that alpha must be an integer. So that ends the reverse direction. Okay, so now let's look at this. We want to show that if alpha is the reciprocal of an integer, so 1 over m, where m is an integer, then z to the alpha takes exactly m different values. Okay, so let's see maybe how we can do this. Let's calculate z to the 1 over m. That's alpha in this case. And we'll notice that that is e to the 1 over m times this principal log of z, and then e to the 2 pi I, and then let's see, we have n over m. But looking at this, we see that this object right here is a root of the polynomial. Maybe I'll call it w to the m minus 1, but there are exactly m roots of this polynomial because it is of degree m. Now that's maybe one like quick way to look at it. Another quick way to look at it is that we get different values of this thing boxed in green for n between 1 and m minus 1, and then they start repeating. So again, we only have exactly m values. Okay, so now that we've seen a couple of basic results, let's look at some neat examples. Now we're going to look at the very classic question of what is I to the I? And so this has been done in like standalone videos many times, but this fits very classically into this portion of a complex analysis course. Okay, so let's do the calculation using this definition over here. So we have I to the I is going to be the same thing as E to the I, and then we have log I times E to the 2 pi I times n. So what I've done is I've just replaced alpha and z with I in this case. Okay, so now let's get to simplification here. So let's see that this is going to be e to the I, and then the log of I is the natural log of the modulus of I. So I'll write that down, plus I times the argument of I, but the argument of I is pi over 2. That's because that occurs in the positive imaginary axis, which is an angle of 90 degrees from the positive real axis. So just to reiterate, this pi over 2 is the argument of I. We saw that in previous videos. And then here we have this is times e to the minus 2 pi n, because I times I is -1. Okay, so now let's simplify a bit. So the modulus of I is 1, natural log of 1 is 0, so that simplifies. And now we have I times I, which is -1 again, and then we can put these two exponentials. So we have e to the minus pi over 2 minus 2 pi n. So those are infinitely many values of I to the I. So maybe the principal value would be the case when n is equal to 0, which would be e to the minus pi over 2, which I think is maybe the most classic result if you were to look this up in some sort of pop math video, is that an imaginary number to an imaginary number is a real number, which is interesting in itself. Okay, so now that we've done this, let's look at functions that are defined by this power structure. Okay, so like I said, now we're going to look at the function z to the alpha. And I want to notice if z is not an integer, then z to the alpha is not continuous. We'll explore this a little bit more carefully so that we can see that. But that means we need to make a branch cut, much like we did in the logarithm case and the square root of z case, which is actually a special case of this setup. And the branch cut that we will make is along the positive real axis. So let's look at, like I said, the branch of the, actually it's the non-negative real axis removed. So we'll look at c minus the interval from 0 to infinity. So let's maybe sketch that up. So here's my complex plane. I'm going to remove the origin, and I'm removing this entire positive real axis. So it looks something like that. And now let's suppose that we write z in polar form. So it's r e to the I theta. And the drawing that I make is what happens in the image of z to the alpha. So just to reiterate what's going on here, we have z to the alpha will be equal to r to the alpha e to the I alpha theta. Okay, so let's put a circle of radius r here centered at the origin. So that's going to look something like this. And then let's look at the image of the points along this circle under this map. So I won't draw them in another complex plane. I'll just kind of notate that we're looking at the image. Okay, so for instance, if we start on the graph right here, so let's say this is going to be something of the form r e to the I theta, so that means its image is r to the theta e to the I alpha theta. Like that. Let's notice as we push along this direction of the unit circle, we're going to approach just r to the alpha. And that's because in that direction we have theta approaching 0. Okay, now let's compare that to something that's happening over here. So here, again, we have something which is r to the alpha e to the I alpha. I'll reuse theta again. But if I approach from this direction, my theta is approaching 2 pi instead of 0, which means this is approaching something that looks like r to the alpha, e to the I, alpha times 2 pi. But if z is not an integer, then these are not equal to each other. So we have this r to the alpha is not equal to r to the alpha times e to the I 2 pi, which shows us why we cannot appropriately define our power function z to the alpha at this positive real axis, because there's like a big question mark of what should we do in the image of this real axis. So the answer is to make a branch cut like we've done. And this branch cut could really be made anywhere emanating from the origin, but I think maybe the standard place to make it is along this positive real axis. And furthermore, the kind of difference between this r to the alpha and this r to the alpha e to the I 2 pi is known as the phase factor. So here, this phase factor of our function z to the alpha at z equals 0. You might say, well, why do we say at z equals 0? That's because it's along a circle which is centered at the origin. And we're kind of approaching 2 points on that branch, or the same point on that branch from 2 directions of this circle, but not getting equality. So anyway, the phase factor is the difference between these. And I don't mean difference like subtraction. I mean what's missing from the red one that appears in the blue one, and that would be e to the I alpha 2 pi, like that. Okay, great. So let's get rid of this and look at a little bit more of a stronger result regarding phase factors in these kind of branch cuts. Okay, now we're going to look at the following lemma, which expands upon this notion of a phase factor. So let's start with g of z being a single valued function, and f of z is the product of z minus z naught to the alpha times g of z. Then f of z has a phase factor of e to the 2 pi alpha I at z equals z naught. So what I mean by that in particular, so if we have a circle around z naught and we approach a point on a ray emanating from z naught from one direction versus another direction, we will be off by a factor of e to the 2 pi alpha I. And that just follows from exactly the type of calculation we did on the last board. So in this case, you could take a branch cut along this ray, although that branch could be along any ray from this z naught point. So now let's look at a more specific example. So now let's look at a little more concrete of an example. The example I want to look at is f of z equals the cube root of z minus 1. Let's notice that that is z minus 1 to the 1/3 power. So it is indeed of this form. So what I have, I've got my complex plane here. I've removed the point 0 as well as everything along the real axis that is larger than 0, kind of in parallel to what we did with our branch cut before. Then I've drawn a circle of radius 1 centered at 1. So let's notice I've removed the point 1 from the complex plane as well as everything to the right of 1 along the real axis. And then I've also drawn a circle of radius 1 which is centered at 1. Notice everything along this circle has the form e to the I theta, as theta goes between 0 and 2 pi. Then let's see what happens when we plug this into our function. So if we map this under the function f, we'll notice we get to subtract this 1 off, and then we have e to the I theta over 3. Okay, and now let's have this function approach this number 2 from 2 directions. So let's approach from this kind of above direction. So that's going to be as theta approaches 0. But notice as theta approaches 0, here we'll get e to the I 0, which is 1. So here we have f of z is approaching the number 1. So that would give us some motivation to say f of 2 is equal to 1. Which makes sense because 2 minus 1 to the 3rd would be 1 from like a calculus class. Now let's see what happens as we approach from this direction. So that means theta is approaching, let's see, 2 pi, but that means f of z will be approaching something else. It'll be approaching e to the I 2 pi over 3. But let's notice that this is not equal to 1. So we've got another perspective value for f of 2, which is different from our first value. Just giving some motivation for this function being multi-valued. But we're not quite done yet. Notice that we could approach 2 one other way, and that would be via another loop. So that would be like theta is approaching 4 pi, and that would give us something like f of z is approaching e to the I 4 pi over 3. And that's not equal to 1, and it's not equal to this other value of f of 2. So those would be like our 3 values of f of 2 in this case. Okay, so let's jump into another example. So now let's look at the function which I'll call f of z, which is the square root of z times 1 minus z. Now I can rewrite that as the square root of z times the square root of 1 minus z. Now let's look at the component functions here. So the square root of z has a phase factor of -1 at z equals 0. That's because e to the 2 pi I over 2 is e to the I pi, which is -1. And so let's notice that that means that if we approach this number 1 along the positive real axis from above along an arc versus below on an arc, our square root will approach 1 or -1. So that makes up for our phase factor. Then furthermore, square root of 1 minus z is essentially the same kind of thing, just shifted over 1 unit. So this has a phase factor of -1 at z equals 1. And here we can see if we approach the number 2 from the arc above, this square root of 1 minus z will approach I, whereas if we approach it from the arc below, it will approach -I. So that's going to be that phase factor of -1. Okay, so now let's put this all together. Okay, so putting this together, we'll see that between 0 and 1, we pick up a phase factor of -1. So that's contributed just from this square root function. So let's maybe notate that as follows. So if we've got a point, maybe I'll call it z1 here. Then from this direction, this is approaching, I'll call it f of z1, whereas in this direction, it's approaching minus f of z1. But if we're outside of this region, for instance, if we're over here, so let's call this z2, then these are going to be approaching the same point, again, because those phase factors cancel. We'll pick up a -1 phase factor from this and a -1 phase factor from this. So that means our branch cut does not need to extend infinitely. It only needs to be along this open interval 0 to 1. And furthermore, since our phase factor is -1, we see that this is exactly 2 valued, which means from this branch cut, we can take 2 copies of the plane and then glue them together. So let's get a picture of that, and then we'll look at several examples in Mathematica. Okay, so now I've got my 2 copies of the plane. So in this first copy of the plane, my function, which is 2 valued like we discussed before, takes on the positive value, but on my second copy, it takes on the negative value. And each of these has branch cuts from 0 to 1. And now we'll glue these 2 copies of the plane together based off of this marking of a plus here, a minus below, a plus below, and a minus above. So now let's draw a path in the combination of these planes to start to visualize how these are glued together. And then, like I said, we'll look at this and a couple of other examples using Mathematica's built-in functionality to look at Riemann surfaces. Okay, so let's say we start over here at this point and we run a path. So maybe our path does something like this. And then it goes through this portion right here. So since these are glued together, it will not immediately appear below this positive real axis. It'll pop out down here. Okay, so let's maybe order these. So this is the first part of this curve. And then this first part goes to the second part of this curve right here. And then this can continue around, maybe it makes some nice loops and edges around here and then goes through this minus portion right here. And then it'll come out this minus portion right here. Maybe it'll do a couple loops and then it goes back to a closed loop right here. So here we've exhibited, maybe I'll label this one 3. So it goes from 1 to 2 to 3, and then 3 and 1 match back up right here. So we've got this closed path in these two copies of the complex plane that have been glued together based off of this function. So now let's jump into Mathematica and look at some visualization of these Riemann surfaces. And then we'll end with a couple of warm-up problems.
Okay, so here I've got 4 examples of plotting Riemann surfaces using Mathematica. So the first thing that you want to do in order to plot a Riemann surface with Mathematica is to import the following function. So you'll just copy this import command from this website. So essentially what it does is it tells Mathematica how to use this Riemann surface plot 3D function. And then once you've done that, well, essentially you just use this function and it will plot your Riemann surface. Now, if you want to look into this function a little bit more, I won't do that in this video, but there are some more options that you can have within the function. But I think this is maybe the standard way to do it, just to get a little bit of an idea of what the Riemann surfaces look like. So for this first one, we're plotting the function square root of z. So as we saw, the Riemann surface was like a 2-sheeted complex plane that was glued together along the branch cut, which was the positive real axis. So we should get some picture that looks a little bit like that, and that's what we get. So we have this spiral up here, but what's happening is we've got this line of intersection, which is like the branch cut, and then what's happening up here is one of the branches of the square root function, and then down here is the other square root of the branch of the square root function. Okay, so now let's look at another one from the video. So here we have w is the square root of z squared minus z, or I guess we looked at z minus z squared in the video, but this should be essentially the same kind of thing. So notice again, we get 2 sheets, but now our branch cut only happens between 0 and 1. As you can see, our branch cut is right here. And then we have 2 sheets that are glued together along that branch cut. So we've got a complex plane going up this way and a complex plane going down that way as well. Now here's a bit more complicated of an example. So we have the square root of z cubed minus z over z to the 4th, or z to the 1/4. So this should have like 4 sheets, and it should be glued together in a pretty complicated way. And as you'll see, that's what we get. We have these 4 sheets that are glued together along multiple branch cuts in really a complicated setup. Okay, then let's do one more. Let's do the Riemann surface of the square root of z times the log of z. So as you recall, the log of z gives us this infinite spiral. So let's see what we get for the square root of z times the log of z. So notice that we still get this infinite spiral, but we also have this collapsing glued together thing happening at the square root of z. Okay, so now we'll move on to some warm-up problems.
All right, so I'll leave you with a couple of warm-up problems. The first is to find all values and plot the following complex number to a complex number situation. So we have I to the minus I to the 1 plus I, and 1 plus I to the I. Next is to determine all of the phase factors of z to the alpha and 1 minus z to the beta. So let's recall the phase factor is not only a multiplier, but it's also a location. Then finally, describe the branch cuts and the Riemann surfaces of these two functions. So we have the square root of z minus 1 over z and the square root of z squared minus 1 over z. And that's a good place to stop.